Okay, so this is the page we were on. I just moved a few things around. I want to keep talking about operations on ideals, meaning if I give you a bunch of ideals, these are some operations you can do on them to make new ideals. Let me remind you of some of the definitions first that we had last time. You have a ring R, a subset I of R is called a two-sided ideal. That was the key definition of R. If x in I and a in R implies xa and ax are in I, meaning you take any element of the ideal and any element of the ring, then the product of these two things in either order is in I. There is a notion of left ideal and a right ideal where you just require this to happen on the left or on the right. And two-sided ideals are also sometimes just called ideals or ideal. Okay. Of course, if R is a commutative, then there is no left or right, so it's the same thing. One special kind of ideal that we looked at, or rather the simplest kind, are what are called principal ideals in a commutative ring. So in a commutative ring R, I is called a principal ideal if it's just all multiples of a particular element. So I looks like A, the collection of all elements of the form A times R, where R varies over R, and A is here a fixed element. So we say that this is the principal ideal generated by A and denoted by A with a round bracket around it. An integral domain in which every ideal is principal is called a principal ideal domain, or a PID. We had this lemma here that Z and Fx, where F is a field, so it's polynomial ring in one variable over a field, these are PIDs, and this at least describes you all the ideals in Z and Fx. So F here is any field. So that's a little recap. So for example, here is a principal ideal in Z, right? 3Z, which means all multiples of 3. And you can check clearly that this is an ideal. Okay, that's more or less a recap, I think. Let's talk a little bit about these operations that we had last time. So if you have a ring R, first of all, intersection of a family of ideals is again an ideal. That's an exercise. Now what that allows you to do is that if you give me any subset of the ring S, then I could take all the ideals containing it and intersect them all, and that's going to be the smallest ideal that contains this S, and that thing is denoted by angle bracket S. In particular, if S is just a bunch of elements x1, x2, xn, a finite set of elements, then this ideal is generated by angle bracket x1, x2, xn. So instead of writing angle bracket around the set, we drop the parenthesis. Okay. Verify, so this is another exercise, that the smallest ideal containing x1, x2, xn explicitly consists of all such elements. You might call them all linear combinations of x1, x2, xn. So you take x1, x2, xn, multiply them by arbitrary elements of the ring R1, R2, Rn, and add them up. So for example, in Z, if you give me three numbers, 24, 36, 54, the smallest ideal that contains them, or the ideal generated by these three elements, is going to be all numbers of the form 24R1 plus 36R2 plus 54R3, where R1, R2, R3 are any integer. Well, by the way, that does not look like multiples of a single number. But here is another exercise. Verify that this is same as 6Z, where 6, you must have noticed, is the GCD of these three numbers. I mean, I can say a little bit about this. 6 can certainly be written as a combination of these guys. Look, 6 is 1 times 24 plus 1 times 36 plus minus 1 times 54. Okay. The GCD can always be written as a linear combination of the numbers, we know that. So 6 is in this ideal I, So all multiples of 6 are also in the ideal I. So that gives you one inclusion, this one, and the other one is also clear. Okay. Maybe once we have that, I can talk about a couple more operations. Where do I write that? Let's get some space here. So even though certain ideals in Z, the way they are presented, may not look like multiples of a single number, we see here that they are. Okay. Like this one didn't look like multiples of a single number first, this I, but turned out to be. Okay. And that's the content of this lemma. We'll do this in a bit. Let me continue with these operations. So the other thing you can do is, given two ideals, you can take their sum or product. Let me explain. So operations continue. More. Let I and J be ideals in R, and let's just say commutative ring. R is a commutative ring. Then I define I plus J is defined to be ideal generated by I union J, meaning it's the smallest ideal that contains both I and J, i.e. it's the smallest ideal that contains both I and J. And the product of I and J is the ideal generated by all elements of the form x times y, where x comes from I and y comes from J. Okay, so practically you can verify that I plus J consists of all these elements. You just need to add an element of I and an element of J. So it consists of all expressions of the form x plus y, where x came from I and y came from J. So what you need to check is that this already forms an ideal. And I know that it's clear that this set definitely contains I and J. On the other hand, if any ideal contains I and J, it's certainly going to contain those guys. And here, explicitly, you verify that Ij consists of all such elements, x1, y1, plus xn, yn, where n is some number, and xi's x1, x2, xn is in I, y1, y2, yn is in J. So you multiply elements of I and elements of J together and add them up. Okay, all such elements form the product. And the sum and product satisfies the usual properties of sum and product. Okay, and this would allow you to construct lots of new ideals. You can take intersections. If I give you a bunch of elements, you can take the ideal generated by them. That's the second operation, if you will. You can take sums of ideals. You can take products of ideal. I just considered sum and product of two things, but you can define sums and products of a set of things. Similarly, define I1 plus ... in, or ik maybe, and the product I1, I2, ik. We'll play with these ideals a little more in exercises.